Welcome to Spring LIB.
Okay, so here we have kind of a geometric problem, and we have two triangles. At point P, we can actually change where P is, but our goal is where should we place P so that theta is maximized? We do have some values for lengths, and I'm going to go ahead and define some extra values. So I'm going to call this theta 1 and this angle theta 2. I'm going to call the distance from A to P x. And therefore, from P to B will be 3 minus x, since the total vertical height is 3. Okay, so I know that I have kind of a straight line where between P, B, and A. So I know that the angle there is 180. So I know that theta 1 plus theta 2 needs to equal 180. I'm going to use radians, so I'm going to just say equals pi. So theta then is pi minus theta 1 minus theta 2. Okay, now we can come up with theta 1 because we can take inverse tan. We have the dimension. So we're going to go minus inverse tan of our opposite, which is 2, over our adjacent, which is 3 minus x. And theta 2 then is inverse tan of opposite, which is 5, over adjacent, which is x. All right, awesome. All right, we want to maximize theta. So theta is our next function. We really want theta as a function of x, which we have now, which is perfect. So now we're going to take the derivative to find critical points. Okay, so the derivative of theta with respect to x is equal to pi, derivative is 0 by power rule. But now I've got to work all these inverse tans. Okay, so yet minus inverse tan in general is 1 over the argument squared plus 1, but we still have chain rule. So the derivative of 2 over 3 minus x is minus 2 over 3 minus x squared, but we get a double negative, so it's plus 2 because of chain rule. And it helps if you rewrite it as twice 3 minus x to the minus 1, then you can see more easily that I will get minus 2, but also another minus 1 because of chain rule, and then the 3 minus x goes to the minus 2 power, which puts it on the bottom. In a similar fashion, we will do minus inverse tan. So the derivative looks like the argument. Oops, that's a 5. Let's make it look like a nicer 5. The argument quantity squared plus 1, and then times the derivative, which is minus 5 over x squared. Okay, so this is kind of messy. And what we're actually going to do is clean it up. And but before I do so, there's some natural cleaning up that happens, because if you look on the first term, I have 3 minus x squared, but that will cancel out the 3 minus x squared on the bottom there. So let's clean this up. I get a negative 2. The first term denominator goes away, so I'll get 4 plus, and then 3 minus x squared. So it actually cleans up quite nicely. Then on the other one, similar thing, I get that cancellation of this term and that term, because when I distribute, it will cancel. So I get minus 5, double negative, so plus 5 over 25 plus x squared. So kind of scary, but not so bad. Okay, but what's scary now is we're actually going to do a common denominator. Okay, so on the left, I'm going to multiply by this denominator, top and bottom. And on the right, I'm going to multiply by this denominator, top and bottom. And so I'm going to do common denominator. So the bottom will have this whole denominator then multiplied together. Okay, so I'm going to do the minus 2 times the right denominator, and I'm going to distribute. So I'm going to get minus 50 minus 2x squared. And now 5 goes times this denominator. So I'll get, and I'm going to distribute, plus 20 plus 5 times 3 minus x. X squared is, 3 minus x squared. Okay. Next, I've got to clean this up in foil. So I'm kind of starting to need some room. So I'm going to erase what's on top and just keep going. But I will keep the very bottom so that we know what we're working with. And I'll remind ourselves what we're trying to do. But we need to just keep going here because there's lots of work to solve this. And I need room on my board. Okay, so let's keep going. We are now basically going to continue at the top. Okay, so I am going to, and this, by the way, was d theta dx. So d theta dx is, let's see if I can clean this up. I'm going to have to FOIL out that term there. Okay, so I'm going to go ahead and FOIL it out. I'll get 9 minus 6x plus x squared. A lot of work for this problem. All right, all over the nice big. I think this is supposed to have a parenthesis here, so that parenthesis goes there. Wow, okay, lots of work for this problem. Okay, so now I can distribute the 5. I'll do that below. We need a lot of room here. So I'll get minus 50, minus 2x squared plus 20 plus 45, because I can now distribute the 5 to each part, minus 30x plus 5x squared. And then I still have my really big denominator. Okay, so finally we can clean this up to try to get a simple quadratic. Let's see, let's look at all the squared terms. I have 5x squared minus 2x squared. So that gives me 3x squared. And then I have minus 30x. And that's that one. And then I got to clean up minus 50 plus 45. So minus 5 plus 20. So that's plus 15. Woo, getting there over the denominator. Okay, we need to set this equal to 0 for our critical point. And I'm going to now clean up the bottom so we can just keep going. Okay, so this was quite a bit of work, not something you could do really fast. Okay, so to make the top equal 0, I'm going to just focus on the numerator now. So let's do that. So I can factor out a 3. That'll give me x squared minus 10x plus 5 equals 0. It'd be nice if we could factor, but I'm not seeing a nice factoring. So we're going to use quadratic formula to get our x. This was a lot of work for this one. Let's do it. Okay, x then is minus b, so 10 plus or minus square root of b squared minus 4 times a times c, all over twice a. All right, so we get 10 plus or minus square root of, let's see, it looks like 100 minus 20, so that is 80 over 2. And that, so 5 plus or minus 80, I can do 16 times 5, so 4 root 5 divided by 2, so 2 root 5. Okay, so that is our x. We can't choose the plus value because that's too big. We can't have x bigger than 3, so we're going to have to choose the minus value. So the one that makes sense for us is x minus 2 root 5. So if I do 5, let's make that a little bit cleaner. Let's go back. So if I choose 5 minus 2 root 5 and plug in the calculator, I get 0.53. Woo, okay, so we have found that our possible max theta is at 0.53. We should do a quick sign chart to double check because we need theta prime to be going from plus to minus. Let's check real quick. So at 0.53, that does make our d theta dx go to 0. Let's look at our equation. The denominator is positive, so we're really just looking at the numerator. If I make x really big, like 100, you can see right away that I get a positive value here. If I make x 0, I get let's see. Something is, oh, never mind. I put in too big of a value because we do have another critical point, and even though it's not physically possible, when I'm doing my plugging in, I have to basically keep less than 3. We can't have 3 bigger than 3. So let me pick something smaller like 1. If I plug in 1 for my numerator, I will get a negative, because I'll get 1 inside here. I get 1 minus 10, so minus 9 plus 5, that's negative. If I plug in 0, I do get a positive. So I do get a max. I do have a max because d theta dx goes from plus to minus at x equals 0.53, which is a critical point. So that is where we can place our p. So p from A should be 0.53. And that's the distance that will maximize our theta. So anyway, that was pretty cool. Good to know. So anyway, hopefully that helped. Have a wonderful day.